There's this aforementioned wonderful blog post on the surreal numbers, and there's quite a simple surreal number generation process that can basically construct all numbers. So maybe this is a good spot to ask, what are surreal numbers and what is the way we can generate all numbers?
So the surreal number system is an amazingly beautiful mathematical system that was introduced by John Conway.
Rest in peace, one of the great mathematicians ever.
Yes, absolutely. And I really admire his style of mathematical thinking and working in mathematics. And the surreal number system is a good instance of this. So the way I think about the surreal numbers is what it's doing is providing us a number system that unifies all the other number systems. So it extends the real numbers. Well, not only it extends the integers, the natural numbers and the integers and the rational numbers and the real numbers, but also the ordinals and the infinitesimals. So they're all sitting there inside the surreal numbers. And it's this colossal system of numbers. It's not a set even, it's a proper class, it turns out, because it contains all the ordinal numbers. But it's generated from nothing by a single rule. And the rule is, so we're going to generate the numbers in stages, in transfinite sequence of stages. And at every stage, we take the numbers that we have so far, and in all possible ways, we divide them into two sets, a lower set and an upper set, or a left set and a right set. So we divide them into these two sets so that everything in the left set is less than everything in the right set. And then at that moment, we create a new number that fits in the gap between L and R. Okay? That's it. That's all we do. So let me say it again. The rule is we proceed in stages, and at any stage, then, in all possible ways, we divide the numbers we have into two collections, the left set and the right set, so that everything in the left set is less than everything in the right set. And we create a new number, a new surreal number that will fit in that gap. Okay, so for example, we could start. Well, at the beginning, we don't have any numbers. We haven't created anything yet. And so, well, we could take nothing and we could divide it into two sets, the empty lower set and the empty upper set, the two empty sets. And everything in the empty set is less than everything in the empty set because that's a vacuous statement. So we satisfy the conditions and we apply the number generation rule, which says we should create a new number. And this is what I call the big bang of numbers, the surreal genesis, when the number 0 is born. 0 is the firstborn number that is bigger than everything in the empty set and less than everything in the empty set. Okay, but now we have this number 0. And so therefore, we now can define new gaps, because if we put 0 into the left set and have an empty right set, then we should create a new number that's bigger than 0 and less than everything in the empty set. And that number is called the number 1. And similarly, at that same stage, we could have put 0 into the right set. And so that would be the firstborn number that's less than 0, which is called -1. So now we have three numbers, -1, 0, and 1. And they have 4 gaps, because there could be a number below -1, or between -1 and 0, or between 0 and 1, or above 1. And so we create those 4 new numbers. The first number above 1 is called 2. The first number between 0 and 1 is called 1/2. And then on the negative side, we have -1/2 and -2, and so on. So now we have, what is that, seven numbers. So there's 8 gaps between them. So at the next birthday, they call them, the next stage, will be born all the numbers between those gaps, and then between those and so on. And as the days progress, we get more and more numbers. But those are just the finite birthdays, because, as I said, it's a transfinite process. So at day omega, that's the first infinite day, we're going to create a lot of new surreal numbers. So every real number will be born at that stage, because every real number fills a gap in the previously born rational numbers that we had just talked about. It's not all the rationals, because actually the rational numbers that are born at the finite stages are just the rationals whose denominator is a power of 2, it turns out. Those are called the dyadic rationals. So the real numbers are all born on day omega, but also some other numbers are born on day omega, namely the ordinal omega itself is the firstborn number that's bigger than all those finite numbers. And minus omega is the firstborn number that's less than all those finite numbers. But also we have the number epsilon, which is the firstborn number that's strictly bigger than 0 and strictly less than all the positive rational numbers. So that's going to be an infinitesimal number in that gap, and so on. On day omega plus 1, we get more numbers, and then omega plus 2, and so on. And the numbers just keep coming forever. So this is how you build the surreal number system. And then it turns out you can define the arithmetic operations of addition and multiplication in a natural way that is engaging with this recursive definition. So we have sort of recursive definitions of plus and times for the surreal numbers. And it turns out you can prove that they make the surreal numbers into what's called an ordered field. So they satisfy the field axioms, which means that you have distributivity and commutativity of addition and multiplication, and also you have reciprocals for every non-zero number. You can divide by the number, so you can add and multiply and divide and subtract. And furthermore, you can take square roots. And furthermore, every odd degree polynomial has a root, which is true in the real numbers, because if you think about, say, a cubic or a fifth degree polynomial, then you know it's going to cross the axis because it has opposite behaviors on the two infinities, because it's an odd degree polynomial. So on the positive side, it's going to the positive infinity. On the negative side, it would be going to minus infinity. So it has to cross. So we know in the real numbers, every odd degree polynomial has a root. And that's also true in the surreal numbers. So that makes it what's called a real close field, which is a very nice mathematical theory. So it's really quite interesting how we can find copies of all these other number systems inside the surreal numbers.
But the surreal numbers are fundamentally discontinuous, as you write about. What are the consequences of this?
Right. So the surreal numbers have a property that they form a non-standard model of the real field, which means that they provide a notion of infinitesimality that one can use to develop calculus on the grounds of Robinson's non-standard theory that I had mentioned earlier. But they don't have the least upper bound property for subcollections. So there's no set of surreal numbers, no non-trivial set of surreal numbers has a least upper bound. And there are no convergent sequences in the surreal numbers. And so for the sort of ordinary use in calculus based on limits and convergence, that method does not work in the surreal numbers at all. So that's what I mean when I say the surreal numbers are fundamentally discontinuous. They have a fundamental discontinuity going on. But you can still do calculus with them because you have infinitesimals if you use these non-standard methods, the infinitesimal-based methods to calculus. And people do that. I once organized a conference in New York, and we had John Conway as a speaker at that conference, and there was a question session, and someone asked him, I mean, it's a bit rude question, I think, but they asked it, and the question was, what is your greatest disappointment in life? I mean, I would never ask a question like that at a conference in a very public setting, but Conway was extremely graceful, and he answered by saying that the surreal numbers, not the numbers themselves, but the reception of the surreal numbers, because he had ambition that the surreal numbers would become a fundamental number system used throughout mathematics and science, because it was able to do non-standard analysis, it was able to do calculus, it unified the ordinals and so on. And it's such a unifying, amazing structure, beautiful structure with elegant proofs and sophisticated ideas all around it. And he was disappointed that it never really achieved that unifying status that he had the ambition for. And this he mentioned as his greatest disappointment.
Yeah, Donald Knuth tried to celebrate it, but never quite took hold.
So I don't want to give the impression, though, that the surreal numbers are not widely studied, because there's thousands of people who are studying it. In fact, Philip Ehrlich, who is one of the world experts on the surreal numbers, mentioned to me once that Conway was his own worst enemy with regard to that very issue, because in the Conway style, everything is a game. And he treated the surreal numbers as a kind of plaything, a toy. And maybe that makes people not take it seriously. Although my view is that it is extremely serious and useful and profound. And I've been writing a whole series of essays on the surreal numbers for my Substack at Infinitely More. And I just find the whole subject so fascinating and beautiful. I mean, it's true. I'm not applying it in engineering, which maybe was part of this Conway ambition.
And I just wanted to, before I forget, mention the Conway turning everything into a game. It is a fascinating point that I didn't quite think about, which I think the game of life is just an example of exploration of cellular automata. I think cellular automata is one of the most incredible, complicated, fascinating. It feels like an open door into a world we have not quite yet explored. And it's such a beautiful illustration of that world, the game of life, but calling it a game. Maybe life balances it, because that's a powerful word. But it's not quite a game. It's a fascinating invitation to an incredibly complicated and fascinating mathematical world. I think every time I see cellular automata, and the fact that we don't quite have tools, mathematical tools, to make sense of that world, it fills me with awe. Speaking of 1,000 years from now, it feels like that is a world we might make some progress on.
The game of life is a sort of playground for computably undecidable questions, because, in fact, you can prove that the question of whether a given cell will ever become alive is computably undecidable. In other words, given a configuration and you ask, will this particular cell ever, be alive in the evolution? And you can prove that that question is equivalent to the halting problem. It's computably undecidable. It's semi-decidable in the sense that if it will become alive, then you will know it at a finite stage, because you could just run the game of life algorithm and let it run. And if it ever did come alive, you could say, yeah, it was alive. But if you've run it for 1,000 years and it hasn't come alive yet, then you don't necessarily seem to have any basis for saying, no, it won't ever come alive. If the behavior was very complicated, maybe if you have a complete understanding of the evolution of the behavior, then you can say no, but you can prove you won't always have that understanding, precisely because the problem is equivalent to the halting problem.
And nevertheless, when you sit back and look and visualize the thing, some little mini cellular automata civilizations are born and die quickly, and some are very predictable and boring, but some have this rich, incredible complexity.